In this lecture, I will discuss simple harmonic motion and elasticity. Consider a spring with certain length that has one free end and the other end is attached. When the spring is left on its own without any external forces acting on it, the spring will have certain length, which we can call unstrained length or relaxed length. And we say that the spring is in equilibrium. Now, if external force is applied on the spring, for example, the spring is being pulled by this external force, Fx applied, and is going to make the spring to stretch by a certain distance x. The same external force can be applied to compress the spring, and then the spring will compress by the same length x. And so there is a relationship between the applied force and the length by which the spring is going to compress or stretch. And this relationship is given by this formula here. The applied force is equal to this coefficient of proportionality, which is known as the spring constant, K, times the length of compression or stretch of the spring. The spring constant is calculated as the applied force divided by the distance by which the spring is stretched or compressed. And so the force has units of newtons. This length x has units of meters. Therefore, the units for the spring constant are Newton meters. So the spring constant tells us how much force must be applied for the spring to be stretched by a certain amount. That's all it does. So springs with large spring constant are thick springs that are hard to stretch or compress, and springs with small spring constants are springs that are easy to stretch or compress, and those are small thin springs. The spring constant also depends on the material from which the spring is made, and so that also determines this relationship here. An important question can be raised. Given a certain spring with a certain spring constant, if this spring was cut into smaller pieces, and for simplicity let's make these pieces to be of equal length, would those individual pieces have the same spring constant as the original spring, or will the spring constant be smaller or larger? And the answer is that the spring constants of the smaller pieces will be actually larger than the spring constant of the original spring. So for example, here we have the spring with the original spring with certain length, and it has a spring constant of K. And then this spring is cut in two equal pieces with the same length. And it turns out that the spring constant of each of those pieces is twice the spring constant of the original spring. If the length of the spring was doubled here, then the spring constant of the new spring would be half of the spring constant of the original spring. So I talked about the applied force that causes the spring to stretch or compress, but we know that once you push on a spring, the spring also applies force on you, on your thumb or your finger, trying to get back to its unstretched length or equilibrium length. This force is known as the restoring force, and the restoring force is defined by Hooke's law. The restoring force is always opposite to the applied force. So here a person is pushing on an object that is connected to the free end of the spring with the applied force to the left, and the spring on its own pushes in the opposite direction with a restoring force, Fx, which is equal in magnitude to the applied force and opposite in direction. And so the restoring force, Fx, is related to the amount of compression or stretch of the spring as minus the spring constant. So the restoring force is equal to minus the product of the spring constant and the stretch or compression of the spring. The restoring force always acts in opposite direction to the direction of the applied force. So if the spring is stretched past the equilibrium position, then the restoring force is going to try and pull the spring back to the equilibrium position. If the spring is compressed past the equilibrium position, the restoring force is going to push the spring back towards equilibrium position. So here is the spring in unstretched state. Then applied force Fx is applied on the spring to stretch it a distance x from the unstretched length. We know that the applied force is equal to the product of the spring constant and the amount of stretch. At the same time, the spring is pulling back towards equilibrium with the restoring force Fx, which is equal to minus kx. The opposite case can be presented as well. The applied force is compressing the spring. The applied force Fx applied is equal to kx. The spring is pushing back towards equilibrium with the restoring force Fx, which is equal to negative kx. Notice that in both cases, the restoring force is at 180 degrees with respect to the displacement of the spring. So here, the spring displaces to the right, the force is directed to the left. Here, the spring displaces to the left, the force is directed to the right. So the minus sign here indicates that difference in directions. Now let's consider a horizontal frictionless surface on which we have a block with mass m that's connected to a spring. The spring has its other end connected to a wall, and a force is applied to compress the spring by a certain amount. We know that the spring is going to push back with the restoring force Fx, and if the applied force is removed, the block is going to start to move to the right. Once the block reaches the equilibrium position here, the block is not going to stop because it has mass, it has inertia, and we know from Newton's first law, it does not want to stop moving the way it was moving unless net external force acts on the block. There is no net external force here because the applied force is gone and there is no friction. So therefore, the block will continue past the equilibrium position, and ideally it will reach the same distance on the other side of the equilibrium position as its starting position. So the block will get somewhere here. And the spring will have stretched all the way here. So the block stops at this point, and then there is now restoring force pulling back towards the equilibrium position. So the block is going to start to go to the left. It will overshoot the equilibrium position. Once it passes the equilibrium position, a restoring force appears that pushes it back towards equilibrium, so the block will start to slow down. It will stop right here. The restoring force will push it back. It's going to pass the equilibrium position. Restoring force appears that is now pushing towards equilibrium. That slows down the block. The block stops here. It starts to go back to equilibrium. And so we now have a periodic motion back and forth between those two positions. that theoretically will continue forever if there is no friction involved in this process. Of course, we know that in reality there is always some friction, so this process never continues forever, but ideally that will continue forever. And so this type of motion, where we have this periodic transition from one extreme position to another extreme position, back and forth, is known as simple harmonic motion. Let's look at a different way to describe simple harmonic motion, visualize it and describe it, so we can solve some problems related to it. So here we have a turntable, which we can also call the reference circle for, geometric purposes. And on this reference table, we have a small sphere that rotates as the table rotates, like this. So if I have a source of light that shines in that direction from the side of the reference circle directly at this ball, all I'm going to see if I place a screen right here is the shadow of the ball as a point. So as the ball rotates, on the screen I'm only going to see the ball going left to right. And this is a periodic motion, much the same as the block attached to the spring from the previous slide. The periodic motion is between two positions, two extreme positions, to the left and to the right of the axis of rotation, which passes through the center of this reference circle. And you can think of the center of the reference circle as being the equilibrium position. So then if I have the screen moving vertically up, as this reference circle is in rotation, then the shadow of the sphere will essentially trace a trajectory that looks like that. So if I then stretch the screen, I have a plot of displacement versus time for the shadow of this sphere. And this plot looks like so, which looks exactly like the plot of a cosine function. So then I can say that the displacement x is equal to a times cosine of omega t, where a is the maximum displacement from the equilibrium position, also known as amplitude. So again, a is the amplitude of simple harmonic motion, which the shadow of this sphere undergoes here on the screen, and the amplitude is defined as the maximum displacement from the equilibrium position. So on this plot here of displacement versus time, the amplitude would be this distance, and also it will be that distance. So the displacement between the two extreme positions, between the left and right, or from left to right, is equal to twice the amplitude of the simple harmonic motion, twice the amplitude of the oscillation. If we take a top view at the turntable with the small sphere on it, this is the outlines of the turntable, this is the reference circle. In the middle here we have the axis of rotation. I'm going to use that as the origin of a x and y coordinate system. Here is the screen on which I project the shadow of this sphere as it rotates around the axis of rotation, like so. And now you can see that the displacement of the sphere on the screen will be from equilibrium position to this maximum position to the right, or to the other extreme position to the left, depending on where the sphere is as it rotates. So when the sphere goes around this top half circle, the shadow will be going from right to left on the screen. And then when the sphere is on the bottom half of the circle, then the shadow will be going from left to right on the screen. And so the amplitude of oscillation here will be essentially the radius of this reference circle. Now, in terms of the reference circle, let's say that this mass is right here on the circle. Then the amplitude, which is again the radius of this circle, is the hypotenuse of this right triangle. So then I can calculate the displacement of, as a function of time, of this particle as it goes, this sphere as it goes around the circle, as a cosine of theta. So the displacement x is equal to a, that's the amplitude or the radius of the circle, times cosine of theta. Theta is the angle that the hypotenuse of this triangle makes with the positive x-axis. But now this is rotational motion. We know from before that there's a relationship between the angle of rotation, the angular velocity, and the time it takes to rotate by that much. And so this relationship was that theta is equal to omega times t. And so this motion, of course, is simple harmonic motion. There is no acceleration as this sphere is rotating. So the angular velocity is constant. There is no speeding up or slowing down. So then if I substitute theta with omega t, I get my expression for the displacement as a function of the angular velocity and time. I already discussed the amplitude of the simple harmonic motion. That is the maximum displacement from the equilibrium position. So in the x versus t graph, the amplitude is measured from here to here or from here to here. Another quantity that is used to describe simple harmonic motion is the period of oscillations. So that is the time required to complete one full cycle. So what is one full cycle? If you look at this graph here, you'll notice that the graph is periodic. After certain amount of time has passed, the graph shape starts to repeat itself. So for example, if I look at this point right here and start going along the plot like so, when I get to this point, after that I get the exact same look as where I started. So this is a unique section of the plot which after that starts to repeat itself right here. So the time that it takes for one unique section of the plot to complete is known as the period of oscillation. And so this is the plot for one cycle of the oscillations. So notice that one cycle starts from the equilibrium position, let's say, goes all the way to one of the extreme points, goes back through the equilibrium position, goes back to the other extreme point, and back to equilibrium position. So in terms of the oscillation of the shadow here, we start from this right position, goes all the way to the left, and goes back to the right. That is one cycle. And the time for that motion from here to here and back is the period of oscillation. That corresponds to one full rotation around the axis of this turntable. Now, the period of oscillation can be any length depending on the specific simple harmonic motion. However, another important quantity is how many cycles were completed for 1 second. This is called the frequency of oscillations, F, and it is equal to 1 divided by the period of oscillations. The unit for frequency is hertz, And you may be familiar with that unit because when you tune your radio on a certain radio frequency, you are tuning to that specific number for that radio station. So 105.3 hertz or 100 hertz or whatever. So that is what you are doing. There is also a relationship between omega and F, and that relationship is given as omega is equal to 2 pi times F. Now, since we are talking in terms of frequency, no longer talking about angular velocities here, we're going to rename this quantity omega, and we will call it angular frequency. So omega is the angular frequency of the simple harmonic motion. So this is again related with how many complete rotations can be done for 1 second. The frequency F was how many oscillations happen for 1 second. The angular frequency is how many rotations happen for 1 second. Now I'm ready to also derive an expression for the speed of oscillation of simple harmonic motion. So this sphere, as it goes from one extreme point to the other, it's moving from left to right and then back, from right to left and then back to right and so on and so forth. That happens with certain speed. When the particle is at this extreme position, its shadow is stationary for an instant of time, and then it starts to move with increasing speed until it reaches the axis of rotation, the center of this reference circle. And then as it passes, the speed starts to decrease until the particle shadow gets to this position. When it gets to this position, for an instant, the particle shadow is stationary, and then it starts to speed up towards the center again. When it passes the center, it slows down until it's stationary here, and so on and so forth, back and forth in simple harmonic motion. So let's say that as this sphere is going around this reference circle, it has tangential velocity of v, and this tangential velocity is directed so that the radius of this reference circle makes an angle theta with the horizontal when the radius is touching the sphere, like so. So since the tangential velocity is a vector quantity, it has an x component and a y component. I am interested in the x component, Vx. So the x component is equal to, Vx is equal to minus Vt times sine of theta. Why the minus sign? Well, the minus sign is because the component points in negative x direction here. And then when the particle gets on the other side of the circle, the x component points in positive x direction, but then the angle, theta, is more than 90 degrees, so the sign will give us a negative number. So this minus essentially takes care of the direction of the velocity depending on where the particle is with respect to the y-axis here. Now let's remember that there's a relationship between linear velocity and angular velocity. So I'm going to use that to relate the linear speed of oscillations with the angular frequency and the amplitude of oscillations. So we know from before that V is equal to R times omega. So in our considerations here, in the context of simple harmonic motion, the radius becomes the amplitude of oscillations, and the angular speed becomes the angular frequency. So the notation is the same, the terminology is different. So therefore, Vt will be equal to A omega, the product of the amplitude and the angular frequency. So then substituting for Vt in the expression for the x component of the velocity, I get minus a omega sine of omega t. And the product of the amplitude and the angular frequency a omega is the maximum velocity with which the shadow of the sphere on the screen oscillates. The maximum velocity is achieved when this sign here is equal to 1. When this is equal to 1, this whole expression has the largest possible magnitude. That happens when the shadow is at the center of the reference circle here, like this. That means that this particle, as it goes around the circle, is right here. So the shadow passes through the equilibrium position like that. And that makes sense because at the extreme position on the right, the shadow is stationary for an instant of time. Then it starts to speed up towards the center. Once it passes the center, it starts to slow down until it stops at the left extreme position. Then it starts to speed up towards the center. It has the maximum velocity of motion at the center. Then it starts to slow down. It reaches the right extreme position where it stops for an instant of time, and so on and so forth. So the fastest speed of motion is when the shadow basically passes through this equilibrium position, this central line right here. So this slide here gives us the general explanation of how to calculate the speed of an object that undergoes simple harmonic motion. So this is a general description of the process of how to figure out the speed of simple harmonic motion. This can be applied for any type of situation where simple harmonic motion occurs, no matter what exactly the object is and how it's moving. As long as the motion is simple harmonic motion, we can actually calculate the speed of oscillation, because if we know the amplitude and if we know, let's say, frequency, then we can calculate everything. So let's see a simple example of how that's applied. The maximum speed of a loudspeaker diaphragm. So we have a loudspeaker which oscillates between two extreme positions to the right and to the left when sound is playing. So the membrane here is basically oscillating back and forth like so, and this is the amplitude of the oscillation. So the frequency of this simple harmonic motion, of this oscillation, is 1 kilohertz, and the amplitude is 20 millimeters. The first question is, what's the maximum speed of the diaphragm? So what is the maximum speed with which the diaphragm oscillates back and forth? And where in this motion does the maximum speed occur? So by definition, the speed of oscillation is equal to minus Vt sine of theta, which we wrote as minus the amplitude times the angular frequency times sine of omega t. And this portion of this definition, a times omega, is the maximum speed. So we are going to work with just that. So the maximum speed is equal to a times omega. Omega we do not know, but we know the frequency of the oscillations, and we also know the relationship between omega and f, and that is that omega is equal to 2 pi times f. So I'm going to substitute omega with 2 pi times f here. And so I have the amplitude, which is 0.2 times 10 to negative 3 meters, times 2 pi times 1 times 10 to the 3 hertz, gives me 1.3 meters per second. So the speed of oscillation is 1.3 meters per second, the maximum speed of oscillation. As I said on the previous slide, the maximum speed of oscillation occurs when the simple harmonic motion passes through the equilibrium position. So when the membrane is right here, that's when it moves with the fastest speed. When it's at its extreme positions, it is not moving at all. It is stationary for an instant of time. So you see how this somewhat confusing or weird-looking expression for speed of oscillations can be applied in a simple problem like that. Now let's talk about the acceleration in simple harmonic motion. So again, I have my reference circle. Here is my sphere that goes around the circle. I'm shining light at the screen, and so I see a projection of the shadow of this sphere on the screen moving left to right in a simple harmonic motion. So my goal is to figure out what's the expression for the acceleration of this shadow as it goes from one extreme position to the other, passing through this equilibrium position here. So for that purpose, I'm going to look at the actual physical sphere that goes around this reference circle. We know that the sphere is under the action of centripetal acceleration directed towards the center of the reference circle. And so this centripetal acceleration has an x component ax, which is what I'm interested in. So using trigonometry, it turns out that ax is equal to minus ac cosine of theta. But now I also remember that the acceleration is related to the angular velocity in a certain way, and that was that the acceleration was equal to the radius times omega squared. So this was for specifically rotational motion. Now in terms of simple harmonic motion, I replaced the radius with amplitude, and omega stays with the same notation, but now it's called angular frequency. And so then the centripetal acceleration is simply equal to a times omega squared. So then I substitute in the above expression, and finally ax is equal to minus a omega squared times cosine of omega t, where the product of a omega squared is the maximum acceleration of this simple harmonic motion. A question can be asked, at what point during this oscillation of the shadow of the sphere is the acceleration maximum? The magnitude of the acceleration is maximum. And so it's very tempting to say that it's right here when it passes through equilibrium position, but that is not true. Because when the shadow is at the right extreme position, it starts to speed up towards the equilibrium position. So it is accelerating. And then when it passes the equilibrium position, it slows down until it stops right here. And then it starts to speed up again. So the maximum acceleration values are actually at the two extreme positions when the particle starts to speed up. And it might be easier to see that if you think in terms of the block attached to the spring. So right here, when the block is at the right extreme position, the maximum amount of restoring force is applied to the block. And so the maximum acceleration that the block experiences is exactly at that moment of time. Once the block passes through the equilibrium position, there is no restoring force acting on it because the spring is not stretched, therefore no acceleration. Once the block passes the equilibrium position, the restoring force pushes backwards, slows it down, and when the block is stationary at the left extreme position, the restoring force is its maximum, therefore the acceleration that acts on this block is maximum, and then the block starts to move the other way. And so you can think of this example similar to the sphere that rotates around the reference circle. If you shine light straight towards the block as you're looking from above, and you place a screen behind the block. So you'll see the shadow of the block going left and right like so. And so this is exactly the same type of motion as the sphere on the reference circle. But it's a completely different system. And so one more time, for simple harmonic motion, the maximum value of the acceleration is calculated as the product of the amplitude and the square of the angular frequency. And this value is observed at the extreme points by magnitude. Now let's discuss the angular frequency calculated for some specific cases of simple harmonic motion. Let's start with a spring that can oscillate back and forth. We know that the spring is under the action of a restoring force, F equal to minus kx. And this restoring force is, from Newton's second law, also equal to m times ax. So m would be the mass of the block attached to the spring. So here is the spring, here is the block. The spring is being pushed to the left. Restoring force pushes it back. It passes the equilibrium position. It stops at this right extreme point, then goes back and forth, back and forth, back and forth. So this is simple harmonic motion. The restoring force is the net force that acts on this block. So this is equal to minus kx. And on the other hand, from Newton's second law, that restoring force is equal to also m times ax. So m is the mass of the block, and ax would be the acceleration that the block experiences. So since this is a simple harmonic motion, I can replace x with its expression that I derived for simple harmonic motion. So this is a cosine of omega t. And the acceleration I can replace with minus a omega squared cosine of omega t. So then this leads to the expression minus ka is equal to minus m a omega squared. So the amplitude cancels out on each side, and then I can solve for the angular frequency. So the angular frequency omega is the square root of the spring constant divided by the mass of the block. So this expression is an expression for the angular frequency of the oscillation that does not involve the frequency of the oscillation. So again, as a reminder, we saw from before that omega is equal to 2 pi times f. And this expression here involves the frequency of oscillation. What if we didn't know that? What if we only knew the spring constant of the spring and the mass of the object that is attached to the spring and it's oscillating, in simple harmonic motion? Well, this gives me a way to calculate the angular frequency of oscillations. And from that I can then calculate this frequency if I wanted to, the frequency of oscillations. I can do one thing further. I can actually calculate the period of oscillations. How? So we know that the period is equal to 1 divided by the frequency, and we know that the frequency is equal to omega divided by 2 pi. So when I combine the two, when I combine those two with this expression, I end up with the following result for the period of oscillations. The period will be equal to 2 pi times square root of m divided by k. So this is also an important relationship that is very useful for problems involving springs and simple harmonic motion. Let's talk now about energy and simple harmonic motion. So this is a screen door, and as you know, there is a spring that is used to close the screen door once it's opened. And so when the door opens, the spring is stretched, and then the spring, or compressed, and then when the door is let go of, the spring is either going to compress or stretch to close the door. This only means that some kind of energy is stored in the spring in order for that process to happen. So what kind of energy is that? Well, the simple answer is that this is elastic potential energy. But how do we calculate it? Well, first we need to look at the work done by the elastic force, or the restoring force. So the work done by this force is equal to F cosine of the angle between the force and the displacement times the displacement. So a simple way to visualize this would be to look at this spring with this mass attached to it. And so the spring initially is stretched to a certain distance from equilibrium, x0, and then it's let go, and at some point it is a different distance from equilibrium. Let's go with xf. So this is the average force that acts on the spring the average force can be simply calculated as 1/2 the value of this force at the two extreme positions, x0 and xf. So this term here, 1/2 kx0 plus kxf, is the calculation of the average force. Then the angle between the force and the displacement is 0, and the displacement is calculated as x0 minus xf, where this sign here appears when in consideration is taken the minus sign for the elastic force. And so after a simple algebraic manipulation of this expression, we end up with this following result for the work done by the elastic force. The work done by the elastic force is equal to 1/2 kx0 squared minus 1/2 kx final squared. So now I'm ready to define elastic potential energy. The elastic potential energy is the energy that a spring has by virtue of being stretched or compressed. For an ideal spring, the elastic potential energy is equal to 1/2 kx squared, where x is the amount of stretch of the spring between two positions, final and initial. So since this is energy, the units we already know would be joules. So let's see how this concept of elastic potential energy applies to a simple problem. We have a 20.2 kilogram ball attached to a vertical spring. The spring's constant is 28 newtons per meter. When released from rest, how far does the ball fall before being brought to a momentary stop by the spring? So the initial position of the ball is right here. It's stationary, then it's let go of, and it falls down, stretches the spring by a distance of h0. The question is, how much is that distance? So this is a question or a problem about conservation of mechanical energy. There is no air resistance, there is no friction forces, nothing like that. So therefore the mechanical energy of this system, spring and mass, must be conserved at all times. So the mechanical energy will be the sum of linear kinetic energy, rotational kinetic energy, gravitational potential energy, and elastic potential energy. All these four added together give us the mechanical energy final. Then on the other hand, we also have that's equal to the mechanical energy initial, which is the initial term for the linear kinetic energy, initial term for the rotational kinetic energy, initial gravitational potential energy, and initial elastic potential energy. So since the motion starts from rest and there is no rolling involved in this process, those two are zeros. Those are zeros as well, and this term here is actually the final kinetic energy, but the both or the mass here stops as it gets to that point. So that's why this final term for the linear kinetic energy is 0. So the kinetic energy terms are zeros. So now let's look at the potential energy terms. The final height is selected to be where the zero reference level for gravitational potential energy calculations is, so therefore that will be 0. So this term here also is 0. Now, the spring starts the process here with unstrained spring. So the spring is not stretched here. That means that the initial elastic potential energy term for the spring is also equal to 0. And so then we are left with only two terms that are not 0. The final elastic potential energy term for the spring and the initial gravitational potential energy term for the spring system. And so, keeping in mind that for the spring, the stretch is essentially the same length as the height by which the mass is going to drop, I'm going to substitute yf with h0, And then I end up with this relationship between the elastic potential energy and gravitational potential energy for the system. From here, solving for H0, I get this expression, and substituting the known values, I get that this distance of the drop is equal to 0.14 meters. So those types of problems are actually very simple to do, because there is always the assumption that there is no resistive forces. Therefore, the principle of conservation of mechanical energy always applies, and all you need to do is write all terms in the mechanical energy for the initial conditions and the final conditions, figure out which terms will cancel or will be equal to zeros because of the initial conditions of the problem, and then work with what's left to figure out the answer to the question. Another system that undergoes simple harmonic motion is the pendulum. So a pendulum is a mass that is attached to a massless cable or a string or a rope that can oscillate back and forth between two extreme positions. And so this is a simple harmonic motion that goes like so, back and forth, back and forth, back and forth. And so when the pendulum is made of a small mass m and a string, again, as I said, that is not of negligible mass, then the angular frequency of oscillation can be expressed as the square root of gravitational acceleration divided by the length of this string, so the length L. So this result is not derived in this textbook because the derivation is a little bit beyond the scope of this course, but the final result can be used for problems involving simple pendulum, like so. And from here, one can derive also an expression for the period of oscillations using the fact that omega is equal to 2 pi times the frequency. So from here, the period of oscillations is equal to 2 pi of L divided by G. Notice one very important point. This period of oscillations and also the angular frequency are independent of this mass here. We can have any kind of mass, any value for the mass, as long as the length of the pendulum is unchanged and as long as the gravitational acceleration is unchanged, the angular frequency will always be the same. The period of oscillations will always be the same. So this was simple pendulum. Now we can have a different type of pendulum which is known as the physical pendulum. So this is for a rigid body with mass, and we cannot neglect that. So you can think of, let's say, a meter stick or some kind of rod or a baseball bat that can swing when it's attached to, let's say, one end. So let's look at the features of a physical pendulum. So this is the axis of rotation. This is the center of mass. So then the length of this pendulum will be the distance from the axis of rotation to the position of the center of mass. So here we have the equilibrium position, and the center of mass swings back and forth about this equilibrium position. So then the angular frequency is calculated as the square root of the mass of the physical pendulum, gravitational acceleration, and this length or this distance from the axis of rotation and the center of mass, divided by the moment of inertia of this pendulum. So for example, if this is a rod, then that would be the moment of inertia of a rod. If it's something else, then that would be the moment of inertia of that something else. So of course, the moment of inertia will have to be calculated using the methods that we practiced in the previous chapter. Of course, from here, an expression for the period of oscillations can be derived, and that would be 2 pi square root of phi divided by mgl. So let's look at this simple example of simple pendulum. Determine the length of a simple pendulum that will swing back and forth in simple harmonic motion with a period of 1 second. So I discussed the calculation of the period of simple pendulum. The period was equal to 2 pi square root of L divided by G. And so if I square both sides of this formula and solve for L, I end up with this expression. L is equal to T squared times G divided by 4 pi squared. Substituting the known values, I get that the length of the pendulum is 0.248 meters. The elastic properties of springs or rubber or other metal materials and all kinds of other materials which tend to return those objects made from those materials back to original shape once they were deformed come from the atomic structure of these materials. So here we have a simple model of the structure of a metallic crystal lattice. So we have atoms indicated with those red spheres, and the forces with which those atoms interact with each other are represented with those springs here. So the interatomic forces make these atoms move around their equilibrium positions, and these forces are forces of attraction and repulsion, and so this whole cell here in the lattice oscillates in all kinds of directions due to the action of those elastic forces. These interatomic forces are actually very strong, and so attempting to deform an object made from metals, for example, from some kind of metal, requires a significant amount of external force due to the strength of those interatomic forces. So if such external force F is applied, the original length of such an object, let's say a steel bar, will be changed by amount of delta L. And so there is a relationship between the original length, the change in length, the cross-section area of this bar, and the force that's applied. And this relationship is determined experimentally and is given by that formula here. So the force is proportional to the ratio of change in length to the original length. It's proportional to the cross-section area of the bar, and it's proportional to this coefficient here, which is known as Young's modulus. And Young's modulus has units of pressure, which are newtons per square meter. So the force F here is applied perpendicularly to the cross-section of this bar, and the amount of stretch here is actually very small. Otherwise, the interatomic forces of the crystal lattice will not be strong enough to be able to return this metal bar to its original shape. So one more time, the amount of stretch is small, and this force F is perpendicular to the cross-section of the bar. In this table, you can see the values for the Young's modulus for various materials. For metals, Teflon, nylon, bone. As you can see, this is a rather big number, which means that in order to stretch an object made from one of those materials, a significant amount of force must be applied to an object like that. So here is an example that uses the formula for the force that I discussed on the previous slide. In a circus act, a performer supports the combined weight, 1,080 newtons, of a number of colleagues. Each thigh bone of this performer has a length of 0.55 meters and an effective cross-sectional area of 7.7 times 10 to the negative 4 meters squared. Determine the amount that each thigh bone compresses under the extra weight. So the formula that relates the force that acts on the thigh bone, and the length of the thigh bone and the change in length in the cross-section area of the thigh bone is the formula that I already discussed. The question is, what is the change in length due to that force? So solving for delta L gives us that F times L0 is equal to, divided by Y times A, is equal to, substituting those values in the formula, 4.1 times 10 to the negative 5 meters. So as you can see, the compression of the bone is 40 microns, which doesn't sound like a lot, and most certainly the performer does not feel that physically. Another type of deformation is shear deformation. This type of deformation is not related to stretching or compressing an object. It can be illustrated best by taking a book, like so, placing it on a flat surface, and then placing your hand on it and pushing forward. So that is going to cause the book to deform in such manner. So you can consider the book as made from sheets, which of course it is. And so once you apply the force like so, the sheets will shift with respect to each other, changing the shape of the book like so. So the relationship between the applied force, the displacement here from the original shape, so the horizontal displacement from the original shape, and the cross-section area of the book is given by this formula. The shear force is proportional to the shear modulus, which has units of pressure again, newtons per meter squared. The shear of the book, or in general of the object, delta x, so this is the shear. It is inversely proportional to the thickness of the object, in this case the book, and it is proportional to the cross-section area of the cover of the book, so the top surface where the force is applied. So one more time, the shear force is proportional to the area of the top surface of the object, is proportional to the shear delta x that is produced by applying this force, is inversely proportional to the thickness of the object L0, and the coefficient of proportionality is the shear modulus. The shear modulus has units of newtons per meter squared. So in this table here are some values of the shear modulus for several different materials: aluminum, bone, brass, copper, so on and so forth. As you can see, this is another big number. So let's apply the formula for the shear force in this fun example. If you push tangentially across the top surface with a force of 0.45 newtons on this jello block, the top surface moves a distance of 6 millimeters this way to the right relative to the bottom surface. What's the shear modulus of jello? So the formula that we apply is the formula for the shear force. And solving for the shear modulus, we get F L0 divided by A delta X. Substituting the values known from the statement of the problem gives us 460 newtons per square meter. And as you can imagine, since the shear modulus of jello is very small, and you may know from experience, it's very easy to shear a block of jello back and forth. Definitely not so with a block made of steel. So the shear modulus is extremely important into the science of deformation of objects for various practical purposes. And finally, let's talk about volume deformation and the bulk modulus. So imagine you place a solid object inside water or other liquid. We know that if this solid object is placed at the, deep enough into this liquid, a large amount of pressure will be exerted on the walls of this solid object. So when that is the case, that will lead to compression of the dimensions from all directions of this solid object. So the initial volume of the object will decrease. So this is the initial volume, this is the new volume after all of that pressure was applied. So then I can ask the question, how is the change in pressure, which results in change in volume, how are the two related, the change in pressure and the change in volume? From experiments, it was determined that the change in pressure is directly proportional to the fractional change in volume. The fractional change in volume is calculated as the ratio of change in volume to the original volume. The coefficient of proportionality is the bulk modulus, which also has units of pressure, so newtons per square meter. The minus sign here is important because that indicates that the increase in pressure results in decrease in volume. So when the pressure increases, the volume decreases, meaning final minus initial volume used in the calculation of the change in volume gives us a negative result. And the other way around, when the pressure decreases, the volume increases. So then the change in pressure will be negative and the change in volume will be positive. So this minus sign here is very important. And so here's a table with some values for the bulk modulus for different materials. You can use those values from all these three tables that I showed you when you're calculating problems involving those concepts. Use these values as if you know them. This concludes the lecture on simple harmonic motion and elasticity.